everyone, and welcome back to our weekly STEMdemic podcast with the Physics Society. Here, we find curiosity in solitude. This week, we're going to the submicroscopic level, and I don't mean to look for viruses.
That's right, we're going to the very same quantum realm explored in the movie of the Ant-Man and the Wasp, although we'll be presenting it far more accurately.
I know! When Ant-Man entered the quantum realm, how was he breathing? If he was smaller than the atoms, how did he inhale oxygen molecules?
All right, enough talk. This time, we have managed to make some sense of one of the most mystifying topics in physics, the intangible world of particles.
Imagine this. If you take a coffee cup and break it in half, and then half again, and keep carrying on, where would you end up? Could you keep going on forever? Or would you eventually find a set of indivisible building blocks out of which everything is made?
To find out more about these indivisible building blocks, we are going to invite in our guest speakers to help us understand the standard model theory and how it helps us understand the world we live in.
All right, so to take on this bumpy ride, let's call up Swati.
And just for some comic relief, we'll bring in Karthik.
What is that supposed to mean?
Just kidding. He's another guest speaker for the day, for this subject requires a lot of brain power to grapple with.
Hey Karthik, did you hear about the man who cooled to absolute zero? He's okay now.
I think we should start the discussion before any of our viewers leave.
Actually, Swati's horrible joke reminded me of something mysterious. The Bose-Einstein condensate. You see, we always thought there were 4 states of matter, right? Solid, liquid, gas, and plasma. I mean, knowing plasma is a 4th state of matter is really cool. But what if I told you there are actually 7 states of matter? Yeah. Now BEC, or Bose-Einstein condensate, is the 5th matter.
Exactly.
State of matter.
Karthik, you know what? I've always wanted to make the 5th state of matter.
Damn. That would be insane. To make it, I guess you...
Disclaimer. Please do not try this at home, however bored you may be. We do not want our viewers to die of hypothermia.
Yeah, point. But it's important to know that to make it, we need to cool a group of atoms to 0 Kelvin, which is equivalent to minus 273 degrees Celsius.
Yeah, I realize as much. We need to strip the atoms of any energy whatsoever, so they have nearly no energy to move around. And they come closer, like humans clumping themselves up together when it's cold, to warm each other up. When atoms have a similar state of their energy, they turn more identical and become more and more inseparable as they clump together.
I swear to God, if I were Ant-Man, the quantum realm is the first place I would go.
Trust me, before you can do any of that, I'll squish you.
Karthik, you know that is not how it works. Anyway, once that happens, they follow the Bose-Einstein statistics and flow without resistance as superfluid.
All aboard the International Space Station, possibly the coolest quarantine location, not on Earth. Scientists cooled rubidium atoms to 10th millionth of a degree above absolute zero, producing a BEC in space.
Alright, since you guys like my other jokes so much, it's time for another one.
We didn't.
This is gonna be so
Okay,
bad.
So,
This is gonna
why
be so bad.
can't you trust an atom?
Oh, let me guess, because they make up everything?
That's absolutely right. Okay, ignore him. You can be so dramatic sometimes. If atoms didn't exist, you wouldn't exist, and the world would be a better place.
You realize you wouldn't be there either, right?
Yeah, I mean, even nothing wouldn't be there. So, isn't that cool?
I mean, if you say so. Okay, anyway, we know that atoms are made of protons, neutrons, and electrons. But have you ever wondered what these subatomic particles are made of?
Oh, I know. Quarks, gluons, leptons, muons, Higgs boson, photons.
Okay. Swati, we have to calm down and explain this slowly and thoroughly. Let's start from the beginning. So we know the basics, protons, neutrons, and electrons.
Yeah, despite the fact that we are made of them, we still seem to struggle with what an atom exactly is. But now, we can go back to describing all those precious tiny little particles I was listing at first. Introducing the Standard Model Theory. Now, this may look like another periodic table, but it is very, very different.
Now, guys, quick, name a few forces you know.
Gravity.
Electromagnetic force.
Yeah, these are forces, but there are also forces called the strong and weak forces. The strong force, carried by particles called gluons, is the force that keeps the protons and neutrons intact, as quarks exchange gluons between each other to be held together.
Now, imagine this. You had a group of people that hated each other so much, and you brought them all together. If you leave them like that, obviously they will all run away. But no, this time we're tying them together with a big rope. And this rope is a strong force, and it overcomes the repulsion caused between protons in the nucleus and keeps us and the universe from exploding.
The weak force, however, plays a slightly different role. The weak force governs the decay of nuclei. So if a particle suddenly disintegrates, you know whom to blame.
The smallest particles found are the quarks, and they have 6 types or flavors. So they are up, down, strange, charm, bottom, and top. Protons are made from 2 up quarks and 1 down quark, and neutrons are the other way around, made from 2 down quarks and 1 up quark.
And electrons, well, they aren't made of any quarks at all.
Another type of elementary particle is the boson, and these are made of bundles of energy. Photons are one type of bosons. Gluons are another. The strong force is carried by gluons, and the weak force is carried by W and Z bosons. And this is interesting to note that the electromagnetic force is carried by photons.
And don't forget the gravitons, which are theoretical particles responsible for gravity.
Yeah, we can go on talking about this for hours. We can talk about Z bosons and W bosons and beta decay, but I really want to talk about my favorite particle.
Okay, fine. Here comes the Higgs boson.
Woohoo!
Since you're so excited, here's another joke. The Higgs boson walks into a Catholic church. The priest says, "What are you doing here?" Higgs boson says, "You can't have Mass without me."
Swati, you really need to stop. How do you expect our audience to understand when they might not even know what a Higgs boson is?
Okay, sorry, my bad. Hint, the pun is on the word mass.
Swati, let's just move on.
Fine. In 2012, scientists at CERN discovered evidence of the Higgs boson.
When particles interact with an invisible Higgs field, they're given mass. This is the broad ungulated Higgs mechanism, and all 3 of the scientists that came up with this, their names are in the name of the mechanism. And this mechanism is the one that pervades the universe.
To understand the Higgs mechanism, here's an analogy. Imagine a room full of physicists quietly chattering with each other. They make up the Higgs field. Then a well-known scientist, say Albert Einstein, walks in, creating a disturbance as he moves across the room and attracting a cluster of admirers with each step he takes.
This increases the resistance to his movement. In other words, he acquires mass, just like a particle moving through the Higgs field.
And suppose after he leaves, a rumor is spread. It creates the same kind of clustering, only this time it is between the scientists themselves.
In this analogy, these scientists are the Higgs particles.
It's story time.
Once upon a time, 2 insanely dense particles collided, resulting in an explosion. The Big Bang Theory, not the TV show, explains the birth of our universe.
Our whole universe was in a hot, dense state. Even time didn't work the way it does today.
Then, nearly 14 billion years ago, expansion started.
Hey, that sounds like a theme song.
So, just after the Big Bang, the Higgs field was 0. But as the universe cooled, and the temperature fell below a critical value, the field grew spontaneously so that any particle interacting with it acquired a mass. The more a particle interacts with this field, the heavier it is.
Particles like the photons that do not interact with it are left with no mass at all. Like all fundamental fields, the Higgs field has an associated particle, the Higgs boson.
On 4th of July 2012, experiments at CERN's Large Hadron Collider announced that they had each observed a new particle in the mass region around the predicted Higgs boson.
Now, you might imagine that they discovered this with a huge change in results. But this is what the scientists really saw. Yep, that tiny bump in the graph that you see, that is representative of the Higgs boson.
Now, like I said before, the Higgs boson was found in the Large Hadron Collider. The LHC is a particle accelerator, which may form metahumans if we go according to what Flash shows us. But I'm pretty sure it is wrong.
Yeah, it is always a possibility though. I mean, the function of a particle accelerator is to, well, accelerate particles.
Accelerate particles to 99.98% speed of light. When these particles accelerate in the LHC in a 27-kilometer vacuum tunnel, they collide at certain points, causing them to break. Particle detectors are located to detect new particles and waves produced by the collision.
And that's how new particles are discovered.
So, Karthik, what do we know until now?
Basically, Higgs bosons are the reasons that particles have mass. But that makes me wonder. Now, CERN has discovered the Higgs boson. Now what?
It's time for mass celebration.
Okay, good joke. But we can't ever know for sure how a particle behaves. I mean, when we observe the Higgs particle, they start acting differently as compared to how they usually behave.
Agreed. The standard model assumes that particles exist as point particles. However, quantum mechanics proposes a very different theory.
Yeah. According to quantum mechanics, particles exist in a superposition and then collapse to only one particular position when observed. But this is something I don't want to touch upon as of now because it's just too big to grasp.
Yeah, maybe another time in our next podcast.
Though, you gotta admit one thing. Physics is beautiful.
Ew, Karthik, stop. Physics doesn't deserve this.
Yeah, man, cut it out.
Disgusting.